Hello, and welcome to this presentation, Getting Started with the ZNB3000 Diplexer Measurements. In this presentation, we'll show how to measure the most important performance characteristics of a diplexer using a Rohde Schwarz ZNB3000 series vector network analyzer. This presentation assumes a basic understanding of diplexers, key diplexer parameters, and how these parameters are measured. If you're unfamiliar with this topic, you might want to watch the presentation Understanding Diplexers before beginning this presentation. We'll start with a short review. Diplexers are passive bidirectional RF components with three ports: a low-pass port, a high-pass port, and a common port, sometimes also called a mix port. Relatively wide filters are used to combine and/or separate signals into two different, non-overlapping frequency ranges or bands. These bands are usually far apart, that is, they're separated by tens or even hundreds of megahertz. Diplexers are most often used to enable two devices, transmitters or receivers, to share a single antenna, but they also allow a single device to use two different antennas. In order to combine or separate signals, diplexers must also provide high isolation between their low-pass and high-pass ports. It should also be noted that diplexers often have a fixed configuration. Their frequency ranges, etc., are not normally user-adjustable or user-tunable. Diplexer measurements using the ZNB3000 are standard S-parameter measurements and do not require any special licenses, options, etc. As with most VNA measurements, an appropriate calibration should be performed when making these measurements. In the interest of time, we won't be covering calibration in this presentation. Diplexer measurements are all one- or two-port measurements, and unused diplexer ports should be terminated. Note that it's also possible to use a 4-port ZNB3000 and have all diplexer ports connected to and terminated by the ZNB3000. Using a 4-port ZNB3000 also reduces the amount of cabling when switching between measurement types. Once the measurement is configured, it will run automatically and continuously, with results updated on screen after each sweep. There are three basic diplexer measurements: the insertion loss between each port and the common port, the isolation between the high and low ports, and the standing wave ratio or return loss seen at each port. The first two of these are transmission measurements, that is S21 or S12 measurements, and the third is a reflection or S11 measurement. In the remainder of this presentation, we'll cover each of these measurements step by step. The first step is selecting the type of S-parameter measurement. This is done by going to Trace Measurement S-parameters. For insertion loss and isolation, either S21 or S12 should be chosen. And for SWR or return loss, choose either S11 or S22. We also need to configure the frequency range for these measurements. This can be done under the Stimulus menu. Frequencies on the ZNB3000 can be entered in two ways, either as start and stop frequencies, or as a center frequency and span. Note that the start and stop frequencies of 500 MHz and 2.5 GHz are the same as a center frequency of 1.5 GHz and a span of 2 GHz. There are several other parameters that can be configured if needed. Under the Power Bandwidth Average button, the generator or source power can be changed. This same menu provides access to the IF bandwidth setting, which defines the width of the filter used to measure power at each sweep point. Lowering this value will reduce noise, but will also increase sweep time. For diplexers with very high out-of-band rejection or attenuation, lowering this value may be helpful. And the number of sweep points can also be changed. This is the number of discrete measurement points within the defined frequency range. Note, however, that in most cases, these parameters can be left at their default values when making diplexer measurements. To select how results are displayed, choose Trace and then Format. For diplexer measurements, results are most often shown either as dB magnitude for insertion loss and isolation, or as standing wave ratio. We'll give examples of both formats in this presentation. Markers are a convenient way to analyze traces and obtain numeric results, and these can be accessed via Trace Marker. Up to 10 markers can be placed, and the numeric value for each marker is also shown on the screen. In addition to manually placing markers, two special functions, Marker Search and Target Search, can be used to place markers on specific values, such as the trace max or min, or on user-defined values. For example, a target search can be used to place markers on specified measured or y-axis values. A target value is entered, and that value can be searched left, right, or across the entire measurement trace. Another useful analysis feature is limit lines, which check for values which exceed a threshold within a given frequency range. This function is enabled under Trace Line. The threshold values are entered in the Define Limit Line dialog, and this can be a single value, or it can be broken up into multiple segments. If the Limit Check switch is enabled, a message will be displayed on limit violation, and the violating segments of the trace will be displayed in a different color. Let's use a limit line to compare two diplexers, both of which have a specified SWR of less than 1.25 over the range of 1 MHz to 50 MHz. We configure a limit line at 1.25 and see that the first diplexer port remains below this limit over the entire frequency range. The other load, however, exceeds this limit, and therefore the ZNB3000 not only displays a fail warning message, but also changes the color of the trace segment which lies above the limit line. Now let's cover the three diplexer measurements, starting with insertion loss. This is an S21 or transmission measurement made between the low port and the common port, or between the high port and the common port. Typically, only one of these is measured at a time, and the unconnected port is terminated. In most cases, insertion loss in a diplexer is on the order of a single dB or less over the specified port frequency range, and it will be much higher, but unpredictably so, outside of this range. It's also possible to measure insertion loss in the opposite direction, that is from common to low or to high, without recabling, but generally the results will be the same in both directions. Let's look at a measurement example. In this trace, we're looking at insertion loss from low to common, and by placing markers we can see that loss is generally quite low, less than 0.2 dB over the nominal low side frequency range of 1 MHz to 50 MHz. On the right, we're looking at insertion loss on the high side, over the range of 150 to 500 MHz, and we see that insertion loss is slightly higher, about 0.3 to 0.4 dB. Note that it's not uncommon for diplexers to have different amounts of insertion loss on different ports. Now let's look at isolation. Recall that this is a measure of how much signal leaks between the low-pass and high-pass ports. Ideally, no power would pass between them. That is, there would be infinite attenuation between these ports. Isolation should be measured in both directions, from low to high and from high to low. That is, both S21 and S12 should be measured. As before, the unused port, here the common port, should be terminated. With regard to the frequency range used to measure isolation, this can be done over the entire frequency range of the diplexer, that is the high pass, the low pass, and everything in between. But more commonly, isolation is measured only over the range for each port, and the amount of isolation for frequencies outside of this port range may not be specified or important. Typical isolation values for most diplexers is on the order of mid-tens to high tens of dB. Here we're measuring the isolation between the low port and the high port over the low port's frequency range. We can see that the amount of power that's transferred to or leaks from port 1 to port 2 is quite small. Isolation here is more than 60 dB over the entire frequency range and exceeds 100 dB at the low end. But the isolation from the high port to the low port of this diplexer is not nearly as great, only between 45 and 50 dB over this frequency range, with a pair of positive and negative peaks towards the higher end of the range. The last diplexer measurement we'll look at is SWR, or return loss. The ports of a diplexer should provide a good impedance match over that port's nominal low and high frequency ranges, and this is quantified in terms of standing wave ratio, or, less often, return loss. SWR is an S11 measurement. A signal is sourced into a port, and the amount of reflected power is measured simultaneously. Both unused diplexer ports should be terminated. Measurements are normally made on both the low and high ports, as well as on the common port, but the SWR between these frequency ranges is not commonly specified and tends to be very large by design. In the ideal case, ports will have a very low SWR, around 1.2 or 1.3 or less, over their nominal frequency ranges. In the example SWR measurement on the left, we're looking at the low side port, and we see that SWR is below the specified limit of 1.2 for most, but not all, of its nominal frequency range. On the high side, we see that SWR begins somewhat above the specified value of 1.2, but then falls below this threshold at the upper end of the frequency range. Note, however, that in both cases, the difference between specified SWR and the measured SWR is never more than about 0.15 units, which is a relatively minor violation in practical terms. Let's end with a brief summary. Diplexers are 3-port RF devices that combine 2 signals onto a single antenna, or split a signal by frequency onto 2 different antennas. There are 3 primary diplexer measurements. These are insertion loss, isolation, and SWR, or return loss. All 3 of these can be measured on a ZNB3000 using standard S-parameter measurements, either made on a single diplexer port or between a pair of diplexer ports. In addition, the ZNB3000 supports a wide range of marker types and values, which can be useful in obtaining precise numeric measurement results. This concludes our presentation, getting started with the ZNB3000 diplexer measurements. If you're interested in learning more about diplexers, other network analyzer applications, or about the ZNB3000, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at Rohde-Schwarz.com.